So with the DFT, we're talking about a discrete finite length. Function of k. And let's make that explicit. So if your x of n is of length n, so is its DFT. Except its DFT will be complex. And it's sampled. It's just a sampled version. The way you think of it is that it's a sampled version of the DTFT at omega equals 2 pi k over n. So the DTFT is the intuitive version of what your signal looks like in the frequency domain. The DFT is not intuitive at all, but it just happens to be easy to calculate. The way you think intuitively of what the DFT is it's a sampled version of the DTFT, but that's not how you calculate it. You calculate it using the FFT algorithm. You can calculate it using, in MATLAB, using the notation x, comma, capital N, where n is the length of your DFT, of your desired DFT. So it will zero pad x to make it n long. It doesn't zero pad it with n zeros. It zero pads it to make it n long. And we discussed why that's so important if you want to do convolution using DFTs. We talked about tables. We talked about properties. We talked about symmetries. And in symmetries, the most important symmetry we noticed is that if you've got a signal that is periodic conjugate symmetric, that it can't be conjugate symmetric, right? Because it starts at, your x will always start at 0. So both x of n and capital X of k go from 0 to capital N minus 1. So you can't have anything that's truly symmetric, that's even, if it doesn't have a negative index. So you've got to use this periodic conjugate symmetric, which goes to a real DFT, or periodic conjugate antisymmetric, which will go to a purely imaginary DFT. We talked about the big issue, though, is circular convolution and linear convolution. And circular convolution is just frequency aliased linear convolution. If you have x of n and h of n, and both are of length capital N, then if you convolve those two, circularly convolve those two, that will be also of length n. And notice that's so different than how to create these linear convolutions. Where now, if you've got the same x of n, h of n, both of length n, then the linear convolution is of length 2n minus 1. And you can compute those by taking the inverse DFT of the DFT of your padded x times, oops, I should say times the DFT of your padded h. So in MATLAB lingo, now using any length with in MATLAB lingo, using an x of n of length nx and a h of n of length nh, you could use it by saying your desired n total is going to be your nx plus your nh minus 1. And then your output for your linear convolution would be your inverse FFT of your FFT of x, 0 padded to make it n long, dot times your FFT of your h, 0 padded to make it that same n long. And that will give you your y. It's really crazy that your y will be purely real, even though all these intermediate things will be very, very complex numbers. If you've got a very long values of x and h, it's possible you'll have some rounding off error and you'll end up with almost perfectly real values and then 10 raised to the negative 16th times an imaginary part, which you'll just have to lop off. And what's totally non-obvious is that this is way faster to compute than a linear convolution. All right, last, I need a new page for this. If you want to capture this. And then the last we covered is the Z transform. Big picture, the DTFT is what has the most intuitive sense. The DFT is what's easy to compute. It has the least intuitive sense. And it's also very hard to work with theoretically. I mean, you can see as you sample this, it just gets painful. And then the Z transform is the one that's the theoretically most easy to work with. Its transforms are just very clean, but not easy to compute and not very intuitive either.